Hello, calculus students. If you're watching this today, that means that I'm not in school for today because I'm taking care of my wife and our newborn. So I will be joining you shortly, maybe at the end of this week or next week. But I just want you to know that I will be present in school, and we are going to start off third trimester right now looking at section 7.1, which is a review of differential equations. We're going to dive a little bit deeper, but hopefully you're going to feel pretty comfortable with this material as we move on. To start, I want you to hit pause and then go through this warm-up, determine if each statement is true or false. Okay? So now that you had a chance to go back through it, to talk about these, they're actually, every single one of these statements are true. So the reason why we review these right now is they're all some form of either Algebra 1 or pre-calculus concept that comes up when simplifying some differential equations. So we just want to make sure that if we ever see two exponents being added, you can split them up as the same base, and then we're multiplying. So in this case, e to the x plus y can be split up as e to the x times e to the y. I consider these two here just facts about the natural log. The natural log of e, remember technically there's a 1, and ln and e are inverses of each other, so they kind of reduce each other out, and you're left with 1. And this is a pretty important one to always remember. The natural log of 1 is always 0. If you're not really positive on why that is, think of the graph. Right? If you have the graph of the natural log right here at 1, when x is 1, its output is 0. And then if I wanted to kind of match this graph as well, if I went in and the input was e, then the output would be right here at 1. So this graph is kind of what I use to remember these two facts. What happens on the bottom if I have e to the x minus y? That can be rewritten as e to the x over e to the y. And sometimes you see the arrows like this saying if it's in this form, you can convert it to the exponent form, or vice versa. You can go either way with these, and actually any of these. We do this to help us out. Like we had said before, one way to view this is the natural log and the e are inverses of each other, so they reduce out, and what's left over is x squared. And then same thing here. If I reverse it and I do the natural log of e, those are inverses, and they will undo each other, so you're left with whatever the exponent is. So those are just some fun facts to remember. Watch. Okay, we're going to do some recall pieces here from Algebra 1 and Algebra 2. I don't want you to write this, but this ties into differential equations. So when we talk about variation, remember what we mean by variation. We have something called direct variation. That means that x varies directly with y, or x is directly proportional to y. When you see those two statements, I think of something like this, where x and y are related, and the only thing that makes them different is this constant of variation, they call it. So k is the constant of variation, or constant of proportionality. Now remember, instead of y, we could call it f of x, but when you see direct variation, it's basically y is equal to k times x. All right, well, what is inverse variation? Inverse variation is when y varies inversely. So when you see that inversely with x, or y is inversely proportional to x, that means that they're related, but it's y equals k over x. Or again, y is the same as f of x. So what are some key takeaways here? We're going to get into this in a little bit, but when you see the word rate, all right, rate means derivative. And remember how we write the derivative. Sometimes it's dr dt. It depends on the variables, but we like to write it as a rate. So we have the independent variable on the bottom and dependent variable on top, but rate is equivalent to derivative. And then directly proportional, remember that means multiply. So when you see the words directly proportional, think y equals k times x. If you see inversely proportional, think y equals k over x. So that should be a quick review of Algebra 1 for you. And we're going to show you how to just model situations. Once you get the hang of this, I'll have you pause the video and write this on your own. I wouldn't write this as notes because I don't think you need to in terms of just writing it all out. But how do I model this situation as a differential equation? So Catherine runs around a linear path. Her position is given by the function p of t, where t is measured in seconds, and she starts running since she started running, and p is measured in miles. So we know a couple of things, right? We know p of t is measured in seconds, and then we know that she's running in miles. So I'm thinking right away, if I know a rate, that would be miles per second. All right? During the first second of her run, Catherine's acceleration, so okay, there's something that's interesting. Acceleration is proportional to the cube root of the time. So we got to talk about a couple of things here. Math, as we read math equations, we want to read very literally, right? The word is stands for equals. So the acceleration, well, wait a minute. We know what acceleration is, right? Compared to pt is position, acceleration is a of t. But we're going to set this up here. So what do I know? I know pt is position. Right? And then we know that if I took the derivative of that, so let's call it the derivative of p with respect to t, that would be the velocity, right? The derivative of velocity of position is velocity. So what if I take the derivative again? That's d squared p over dt squared, and that is the acceleration. So when I see that word acceleration, ooh, I don't know what I was spelling right there. Acceleration, I'm going to think of acceleration as the second derivative. Now the word is equals. So I'm going to think the second derivative with respect to the original position, so d squared p over dt squared, that's the equal sign, proportional. Now they don't use the word directly, but proportional is the same thing as just saying, you know what? It has a k value, right? So I'm thinking proportionality is there's a constant k, and then we've got the cube root of the time. So cube root of the time. And then I kind of did this without saying what we're doing. It says write a differential equation that describes a relationship where k is the positive constant of proportionality. So when you see the word proportional, we know there's a constant of proportionality k. And then we just know that that's the relationship. Now, we didn't do anything with this. We just set up the equation. And it takes a while to get used to this, but this is how we model a differential equation situation. Let's try another one. Okay? And if you want to, you could hit pause right now. Since it's multiple choice, you might be able to try this one on your own. But it says, which of the following is a differential equation that could describe this relationship? So we're trying to set up a differential equation again. Well, let's read through this. A scientist is studying the relationship of two quantities, T and S, in an experiment. The scientist finds that under certain conditions, as the quantity S increases, the quantity T decreases. After taking measurements, the scientist determines that the rate of change, there it is, that's the derivative. So the rate of change of the quantity S, let's write that right away. As soon as I see the rate of change, I'm thinking derivative. Well, what is it? It's the derivative of capital S with respect to quantity T, so dt, right? And they use a capital T here, so that's why I'm putting a capital T here. So this kind of rate of change stands for derivative, and that's where I got this information from. The next piece, notice the word is, right? That's a very important word. Is our equal sign right here. And then they tell us that it is inversely proportional. Inversely proportional, that means there's going to be a k value. It's inversely proportional, so we're going to have to divide. Inverse means divide. And we're going to divide by the natural log of the quantity t. we're going to divide by the natural log of t. And now that is my differential equation. And does that match? Which one does that match? So let's see if we have that perfect setup right here. Try this one. This is a somewhat famous style of a problem. It's a rumor. So a rumor spreads. Now I've seen these problems with like a virus spreads, but I don't think they're going to do that because of everything that's going on with COVID right now. So they're going to probably talk about it as like a rumor spreads instead of something else. But a rumor spreads amongst a population of n people. So I'm thinking, okay, n is just the total amount of people at a rate proportional. So notice there's the word rate. So now we've got a derivative dn dt proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. So I'm thinking the word product is important. That means multiply. And what am I going to multiply? The number of people who have heard the rumor and the number of people who have not heard the rumor. So they tell us a little bit more here. So if P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model the situation with respect to time t, where k is a positive constant? Well, look at right away. Every single one of them says dp dt. So dp dt. Now, what is that? That's the rate of p. Well, what does p denote? The number of people who have heard the rumor. So this is the rate at which people have heard the rumor. Well, what is that rate? The rate, which we know the word rate is our derivative, is proportional. So I'm thinking, okay, proportional. There has to be a k value. Notice every single one of these has the k, so that word proportional is our constant of variation. And then what are we doing? Well, we're doing the product. So product means multiply. And what are we multiplying? The number of people who have heard the rumor. Well, wait, P denotes the number of people that heard the rumor. So we're going to multiply P times the number of people who have not heard the rumor. Now that's the interesting part. We know we have a total of n people. So if I take n and I minus p, p is the amount of people that heard the rumor. So that would be the total amount of people minus the people who have heard the rumor. Well, this would be the people who have not heard the rumor yet. And then it's just the product, and product means multiply. So you can see right here, the differential equation that represents the scenario is B. Okay, so that's the first part, just setting up these models, these verbal models. Now would be a good time if you want to take a 2-minute break, pause it, stretch, stand up. Okay, so what about section 7.1? Well, we're classifying ordinary differential equations. And a lot of this is going to seem familiar because it is. We've covered a lot of differential equation stuff already. This is a nice review in case you haven't mastered it. So I don't think you need to write this information down because we've already talked about a good amount of it. But what is this word ordinary differential equation? Well, an ordinary differential equation is an equation involving an independent variable, which is usually some x, and a dependent variable, which is y. And then the derivatives with respect to derivative of y with respect to x. So ways that we can write that. Remember y prime? That's an example of how we can write the derivative. Or I could put dy dx. But all of these are different types of what we call ordinary differential equations, but really just call them differential equations. Why? Well, what is it? It's a derivative that somehow relates the functions. So here we've got another one. P prime equals 7p. You can see that the derivative of p is equal to the equation 7 times p. And then we've got a couple other ones. You've seen these. Now this one's interesting because we have the second derivative and the first derivative mixed together. And that can totally happen. This is a special type of differential equation, and we name them by their order. So what we mean by that is the order of a differential equation is the order of the highest derivative appearing in terms of y or p in this case. So like an example here, I have a y prime. Well, that's a first order. Same thing here, p prime or y prime. All of these first three would be considered first order derivatives. But notice the highest derivative in this equation now is a second derivative because y double prime is the larger derivative within the whole thing. So you can have many, many different orders. It just depends on the highest derivative that's available. Okay. So the next part here is what we've really done a lot of so far. Remember, a function y is equal to f of x, those are interchangeable, is called a solution to a differential equation if, when y and its derivative are substituted into the equation is true for all x's on the domain. We'll talk a little bit more about domain tomorrow, or the next time we visit this, but remember the two types of solutions we had. We had general solutions to a differential equation, which kind of represented the family of solutions where we had the plus c, and a lot of times that was solved by not having any bounds. So when there were no bounds on an integral, that's where we put the plus c, and that represented all possible values because c was just that vertical shift of a function. Then we got more specific, and we called it a particular solution. A particular solution is when you use the initial condition, and then that allows you to find the value of c. So let's say that I had this equation right here as a general solution, and then I told you, you know what? This function actually goes to the point 0, 2. Well, that's the spot where what do? We take the 0 and plug it in for x. We take the 2 and plug it where the y goes. And then notice we can solve for c. E to the 0 is 1. 3 times 1 is 3. Solve for c. And then what do? We take this c and we plug it right back in where c was originally. And now we have one specific equation. It's no longer a family of solutions. It's one specific member or one specific solution. All right? So the condition, the initial condition, kind of bounds this curve not to a family of functions, but to a specific function. All right, so our goal then is to just review a handful of these. I don't think you need to write these down because we've talked about these. I just want to refresh your mind on a handful of pieces. So remember when we see the word verify, you've got to prove. The word verify is almost like the word prove or show that if you know the original equation, we want to verify that this equation is a solution to the differential equation right here. Well, let's look at the different parts. Within this problem, you have to show that the second derivative minus the first derivative and then we know the original function. So it's just substitution. Now you would have to show all this work. I think that's important for us to know. You don't want to skip any steps when you're showing calculus because they want to see this work here. They want to see your substitution. And then it has to be accurate too. If you've got parentheses here, this negative needs to be distributed. So the only way we can do that is if I put parentheses around these pieces. kind of like that -2 here, I'm going to put parentheses around the y, but instead of y, we're going to write the original function. Now, just to make this appear a little nicer, where did these values come from? Those are the things we found: the original function, the first derivative, the second derivative. And then it's just simplifying. What I'm going to do is distribute the negative here. Distribute the -2 here. And then combine like terms. I'm going to pause it and you guys can finish the rest here. All right, so you can see I have my like terms here. I just kind of made this a little more easier to view. The blue terms add up to 0. The remaining red terms add up to 0. And I showed that the left side equals 0 and the right side equals 0. So therefore, I proved that this is a solution. Okay, the other style of problem that we had is verifying that a given function is a solution to the differential equation. So now my goal is to show that this equation right here has this derivative. So I'm going to take the derivative of both sides. Okay. So make this easier. So this is my side work. I'll answer this question a little bit later, but here's my goal. I want to take the derivative of this, and it should end up like this. Now, this is called implicit differentiation. And we covered that a long time ago. It might even have been first trimester. Okay, so what do? We take the derivative of both sides, and we're going to take the derivative with respect to x. And then derivative of a constant is 0. So what we know is we know anything that had just dx reduces down to 1. So those are gone. But now notice these two pieces have dy dx. So I'm going to do two steps at one here. I'm going to take this term and this term, which keep in mind that has a 3 over there. I'm going to bring them both over to this left side. So I'm going to subtract a 2x, and I'm going to add a 3x squared y. Notice how the top kind of matches that. And then what's left over now is this piece right here. This is still on the left side. These two pieces moved over. Well, they both have a dy dx. So I'm going to factor out the dy dx. And then what's left over is a negative x to the third, and then a 12y to the third. Now notice dy dx has been factored out. So now I can solve for that. And I should make it look exactly like this. So see how I have the minus 2x on top? I'm actually just going to write the 3x squared y first, and then put the minus 2x, because I can flip addition around. But now it matches perfectly, and then I'm going to divide by this piece, but I want the 12y to the third to come first, and then minus x to the third. So notice, I have this matching perfectly. So I verified that solution. Okay, quick side note, it says classify the differential equation. Okay, couple other review pieces: classify the differential equation, then find the general solution. So when I see this, I'm thinking right away, I know my answer is going to be plus c. Well, what do we have to do before we well, let's classify this. Notice this is a first order derivative because there's just a 1 here. So this would be a first order. So I'm not going to write it down, but that's how I'd classify it. And then my goal when doing differential equations is I need the dy by itself. So I'm going to actually take and multiply both sides. So that leaves me with dy. I will move this dx over in a second. And then I'm going to put this out front because that's most likely how it would be written anyways. And then this dx, we're going to actually bring it over to this side. And hopefully this is familiar. Your last unit, we tested on this. Because now, what do I have to do? I have to take and find the solution. I have to undo the derivative, which is the integral. So I get y equals, and then we run into a slight problem, but we've got a u substitution. What if I make this part u? Notice what is du? It's 3x squared dx, and I have that right here. So now my new integral is just sine of u du. So I did a u substitution, and now whose derivative gives me sine? The answer to that is negative cosine. And then we could put u plus c, but remember our final answer, we have to have x to the third back in. All right, so nothing crazy there. This is a complete review. This could have been a test question on your last unit. I'm comfortable with that. On the next part, I think I've got a couple of these problems here, is to use the initial value, or this is your particular solution. So you're finding an exact answer, and the key is what is the given initial condition. So notice dy dx, it's almost the same things that we had before, but now find the general and the particular solution. So they want me to find both to the differential equation with the initial value of 6, 0. Remember, that's x, y. That's an ordered pair. So what am I going to do? Well, I'm going to move the dx over to the other side first. And then I'm going to try to integrate both sides. Now, do remember, integration, we know how to do u substitution here. So we might have to do a u substitution to make this easier, which in this case, I'm going to let the bottom 4x plus 1 be u. And then I'm going to take the derivative of that. But I don't have a 4, so I'm going to move the 1/4 over. Okay? And usually I do that in a separate color. But what do we have? Well, this dx is going to be replaced by 1/4 du, but that 1/4 is a multiplier. So I'm going to push that out front. Now we also have an extra 2 here. That 2 is also a multiplier. So I'll push that out front. The only thing that's left over is the square root of u. And then we're going to take the integral of that side. So I took the integral already on this side. Remember, that's just y. So now we're going to go ahead and multiply this out front. Well, that's 2/4, or 1/2. And this, maybe you remember it, but that's the same as u to the 1/2. So if that's u to the 1/2, I'm going to integrate that. I'm going to add 1 up top, which is 2/2, so that gives me a 3/2. But if I put a 3/2 up front, I have to put a 2/3 out in front. And then we're going to put a plus c for now, because we'll get the general solution part has the plus c. Okay. So now, notice the 2's reduce out, so I get a 1/3, and then I get 3/2 c, and whatever u is, we're going to just go right back and plug u back in. So there is my general solution. Now, the only extra work to find the particular solution is we need to use the initial condition to find the C value, right? And we know X is 6 and Y is 0, so I'm going to plug a 0 in right here and a 6 in right here, and then we're going to solve. Now you do want to show proper steps, so I'm going to take my general solution, I'm going to plug a 0 in for the Y, and sometimes you get just points for plugging in and showing that. So it's important that you show that you plugged a 6 in here and a 0 in here, so you can see where the X and Y are. Now here, you don't need to show any other work. If you can do this in your head, perfect. But I know that I get 24, that's 25. And then I know that 25 to the 3 halves, that's the same as the square root of 25 to the third power. So that's 5. 5 to the third power is 125. And then I'm going to times that by 1/3. Well then, let's see, 25. 125 divided by 3 is not perfect, so I'm just going to rewrite that. I don't think that's perfect. Maybe it is. No, it's not friendly, so I'm just going to leave it like that. But I have to solve for C, so I'm going to move that value over, and here is C. So what is the particular solution then? The particular solution is when you take that C value and you plug it into the general equation. So we're almost done. So my final answer is take y equals 1/3 x to the 4 plus 1 to the 3 halves, and then we're just going to add, or in this case we can say minus 125 over 3. Okay. As an extension on this problem, we have this part down here. It says write the equation of the tangent line at the point 1, -1. Well, you don't need much for this. And this is a very common question that is asked. So what do we need? Write the equation of a tangent line at the point. Right? Equation of a tangent line. I need a slope, and I need a point. They gave me the point. Here's x1, y1. So I'm just going to plug that in right away. So y1 is -1. x1 is 1. And then all I need is a slope. Wait a minute, what's another word for a slope? It's derivative. So the derivative has already been given right here. So all I need to do is find that slope using the point that was given. Right? So my slope, which is equal to dy dx, plugged into the value when x is 1 and y is -1. So I'm going to take the equation 2 times the square root of 4x plus 1. Now notice, for this specific differential equation, dy dx means slope. All I need is the x, because there isn't a y in this problem. So my slope is really determined by the x, and then we just simplify it, okay? What is it? It's 2 times the square root of 5, and there's the slope. That's going to go right here. To be honest, we know that this is addition. I wouldn't distribute this. This isn't going to be friendly, but sometimes this +1 might be brought over at the end, and you could stop right there. And there's the equation of the tangent line. Because you were given the point, and once you know a point, you can use that point to find the slope, and dy dx means slope. All right, last problem, then we're done. Particle motion, right? How do things move? Well, a particle moves along the x-axis, so that's left to right, with a velocity of 1 over square root of t when t is greater than 0. At time t equals 1, its position x is equal to 4. So now that's an initial condition, right? You got to think of this. T is the independent variable, so that's going to come first. And then x is the position, so that's going to come last. That's your output. Don't get confused by x being the independent variable. In this case, it's time. So now it says find the acceleration and the position for this function. So I'm going to actually have you guys work through this, and I'm going to pause it and do some of the work. All right, first thing I'm going to do is velocity. I don't love the way this is written, right? I know the square root is the 1/2, and I actually would much rather prefer rewriting this as t to the negative 1/2. Now, acceleration is pretty friendly, right? To find the acceleration, I'm just going to take the derivative of this. So acceleration, which is equal to the derivative of v, is just doing the power rule. Taking the derivative, so I'm going to take 1 away. Now remember, that's like subtracting 2 over 2, which is a negative 3/2. And there isn't a plus c on this because we're taking the derivative. So there's the acceleration equation. Nothing crazy. It's the position that we have to work a little harder. So what did we do to get acceleration? We just took the derivative. Well, what if I go the other direction and I want to work backwards to find position? Position is the integral of this piece. So I need to find the integral of the velocity equation. And officially there'd be a dt there because this is a derivative. So now we know that the integral of velocity is position, which use x of t. And now I'm going to add 1 to the top because we're undoing the power rule. So we're going to add 1 up top. So this will give me x to the 1/2. But if I put a 1/2 up top, I have to put a 2 over 1 out in front. And then I have to put the plus c. So now that I have my general solution, I got to use the position. T is 1 and x of t is 4. So I know if I put in 1 right here, x of 1 is 4. If I put in 1 here, then I'll be able to find c. Well, 1 to the 1/2 is 2. If I bring the 2 over here, 4 minus 2, c is equal to 2. My final position equation is taking this c and plugging it right back in here. So I'm rewriting this exactly, but now putting a 2. Now I have my position function. And how did I do that? I took the integral. Right? So I know position, velocity was given, and I know acceleration. So you can go either way if you know an initial condition for position. All right, the homework tonight is from the textbook. It's section 7.1. Here's the page numbers. And then make sure you do the extra little piece. It's at the end of this section, 4 problems. And make sure you show all your work on a separate sheet of paper. Submit your image to Schoology. The answers are in our Schoology folder, so you can go back and check your work as you go. Have a great day. Adios.